So, we are now on to 26th lecture, and having discussed the oxygen steel making process, it is now time to discuss the other prominent technology, which is the arc furnace steel making or electric arc furnace steel making. So, today and tomorrow, that means the 2 consecutive lectures we will be spending on arc furnace steel making, and then we will wind up our discussion on primary steel making. And as I have indicated, there could be many other processes of steel making, not so popular these days, particularly the energy optimizing furnaces, the Hearth furnace, etc. And I have repeatedly been saying that as far as the principles of steel making are concerned, they are not dependent on the technology of steel making. It is the kinetics that is more dependent. So, let me give you a quick introduction to electric arc furnace steel making. And we know that, and I have said that 30 to 34%, I would say 35%, that is the global steel making through the electric arc furnace technology. And arc furnace, of course, is used in the steel industry for steel making. Arc furnace also is used just as a pure remelting unit in many of the foundries, which want to process liquid metal. So, they do not do any refining, they do not do any processing, they just melt liquid steel in arc furnace. So, that sort of a discussion we are not going to make. We are going to explore steel making in an electric arc furnace. So, 30 to 35% of the total steel produced in the whole world is through the arc furnace steel making, and arc furnace got considerable popularity after the Second World War, particularly because of the large amount of scrap availability. So, scrap and these days DRI, these are the principal raw materials for making steel in electric arc furnace. You must understand here, if you are using scrap, in that case very little refining, unless and until you get your selection of basic scrap is faulty and you have gotten all kinds of contamination in the scrap, then of course some refining is necessary. But if you can sort the scraps properly in the scrap sort yard of an electric arc furnace plant, very little or no refining would be necessary in steel making process. But today the arc furnace traditionally, which has been built for processing or remelting and a little bit of refining of steel, uses quite a bit of DRI, that direct reduced iron, which we have discussed extensively, DRI or the sponge iron production through Midrex, through the cell iron process, etc. And also there is an increasing tendency to use hot metal in the arc furnace. So, quite a bit of development has taken place. There is a competition between the arc furnace steel making and BOF steel making, because I have mentioned that the tonnage and is huge, and the cost of production is also enormously low in the BOF route. Of course, we will see that the energy consumption per ton of steel produced is more there, but arc furnace as such, traditional arc furnace used to take very long refining periods, and so making arc furnace really competitive to BOF steel making necessitated lot of developments, and one such development is the introduction of hot metal into the as a charged iron bearing feed material into the electric arc furnace. So, today's electric arc furnaces mostly will be operated with feed material like containing partly scrap, partly DRI and partly hot metal. And the advantage of using hot metal, as you can see, hot metal contains carbon, silicon, etc. So, additional heat is liberated. There is a chemical heat versus electrical heat cost factor involved in the incorporation of hot metal in electric arc furnace. So, therefore, sometimes if you see that the cost of electricity is too large, everything fluctuates in the market, nothing is stationary. For example, the iron ore price changes, the scrap price changes, electricity price changes. So, today many steel plants in the world, when 30, 40 years back, say I would say, you have, for example, a blast furnace and a BOF converter. But today, in the same premise itself, you have arc furnace, you have mid-rex process, and industries really try to use hybrid steel making routes in order to cost optimize the whole process, because raw material vis-a-vis electricity cost is a very important aspect in the making of steel plant and in constructing modern steel plants. So, if you go to, for example, steel plants like, no steel plants today have only one single route of steel making. If you go to, for example, this the Hazira plant of Nippon Steel and ArcelorMittal, you will find there is a mid-rex process, there is arc furnaces, there are corex furnaces, there are blast furnaces, oxygen steel making and so on, diverse, and you can apply permutation combination in order to find out that for a given period of time, depending on the market scenario, which process you have to integrate to produce or deliver the final product, which will fetch maximum amount of profitability to you. So, we often say that steel making technology has become a hybrid technology now. Okay? So, part of steel could be produced through electric arc furnace, part of steel could be produced through the BOF in the same premises itself. But there is an exclusive class of steel plants, okay, which are small steel plants, which in conventional terminology many people refer to them as mini mills. Okay? And in Indian definition, the mini mills are about maximum productivity could be 1 million ton per annum. That is the maximum productivity. So, and these are special steel plants, and where we have exclusively EAF, and there, because there is no availability of raw material, hot metal, and they are basically the scrap and DRI based plants, and then you have EAF, then you have ladle metallurgy or secondary steel making, and then you have casting. Very simple plant, no blast furnace, no hot metal, and these are small plants not producing the carbon grade of steel. Okay? Carbon steel, for example, they are producing specialized products because their productivity is much smaller. So, they have to produce a value added product, and the cost between the what you call the carbon steel as well as various kinds of special alloy steels are different by a factor of 2 or 3. So, even by producing a very small amount, even by consuming electricity, even not using hot metal, such plants have remained viable because of the simple fact that they could produce a steel which has significantly more market value or worthiness in comparison to the plain carbon steel, which is produced by blast furnace BOF route predominantly. So, these are mini mills or arc furnace based steel plants, and we have about 30 such plants at least in the country operating, where the arc furnaces have capacity from about 25 tons to about 60 ton. That is the kind of. But if you go to integrated steel mills, there the arc furnaces have much bigger productivity. Okay? Simply why they do not have large capacity arc furnaces, because the demand of by a given industry is small. So, 60 ton, 50 ton, 30 ton is a good hit size. Many of the steel plants, you do not require automotive gears of a certain size, at the rate at the level of 200 tons or 300 tons, something like that. So, that is why these furnaces are pretty small, because the customer requirement, the hits requirement or the size requirement or the volume requirement remains to be small. But in the case of plain carbon steel production, so if you go to JSPL Raigad or if you go to Nippon Steel, ArcelorMittal Nippon Steel in Hazira, the size of the arc furnaces tends to be much bigger. Okay? So, we have 30 such plants at least in India to the best of my knowledge, and these collectively produce about 10 million tons per annum of sophisticated steel in India. Okay? So, good chunk of Indian steel comes from integrated steel mills, from the secondary sector or from the arc furnace sector about 10 million tons, and the balance which constitutes our 110 million ton production, current production rate, comes from the induction furnace steel making, which is a very peculiar scenario, and this I am going to address when perhaps in the last lecture when I talk a little bit about the steel making scenario in the country. So, if you take DRI or scrap, you must understand that you do not have much carbon, much silicon left. So, therefore, this is a non-autogenous process, and electric arc furnace basically tells you that you have to supply energy from the outside, but in BOF we have seen that there is no energy which is being supplied outside. The heat is generated because of the chemical reactions, and that sustains the process. Okay? So, although the thermodynamics of steel making are identical, because you are talking about 1600 degrees centigrade, you are talking of close to 1 atmosphere pressure, okay? The reactor maybe 1.5, 1.8, something like that, and so the nature of the chemical reactions, the carbon oxygen reactions, we will write the same set of carbon oxygen reactions even for steel making. Either dissolved carbon will react with dissolved oxygen, or dissolved carbon will react with FeO content in the slag. So, these are the two dominant mechanisms of carbon oxidation in BOF as well as. But despite the similarity of thermodynamics or the chemical reactions in BOF and EAF and other steel making processes, EAF steel making is a class apart in terms of its maneuverability as well as in terms of its ability to process diverse grades of steel. The productivities are different, the sizes are different, the technology itself is different, okay? And we are going to discuss the technology per se. The reactions need not be discussed, but there is a need to understand the technology of steel making in electric arc furnace, which is substantially different in terms of geometry of the vessel, for example, is different. The furnace does not look like the pear shaped converter that I have shown in the basic steel making process. Okay? Similarly, the capacities are different, the refining rates are different. You do not get an emulsion phase as you get in the case of so all these things will be discussed when we will go inside the arc furnace steel making. So, with this background, now let us look at the arc furnace, electric arc furnace in just examine that what are the essential components of an electric arc furnace. So, arc furnace basically, so we will say construction, features and operation. So, we want to briefly address, and as I said that this course I do not want to make it very descriptive in terms of telling you the thickness of the lining or the composition of the lining material, etc., but construction, features and operation of arc furnace. So, as opposed to a BOF converter which looks like a pear shaped vessel, okay, this is our BOF, and EAF is a much more shallow kind of a, it is a it looks like a saucer, and there is so this is the bottom part of the furnace, and there is a removable roof. So, the roof is on a automated arm, and that the roof can be replaced and the furnace interior of the furnace can be exposed. This furnace lining, and this is our EF, this is called the hearth of the furnace, and this is called the roof of the furnace. Our requirements of lining materials are different in the roof as well as in the, because of their exposure. This is not in touch of molten metal, but this comes is exposed to huge amount of heat which is liberated from the system. Now, into it there are electrodes, and these electrodes basically there are, depending on the type of the furnace, and we have two different types of furnaces. One we call as a DC furnace, the other is an AC furnace, and what I have shown here are the three electrodes corresponding to the three phases. So, it is an AC furnace basically, and then what happens is that you have the molten metal here, and there are arcs which is stuck between the electrodes, and this arc produces a temperature which is about 4000 degree centigrade. And from here, this is rarely submerged in the metal, okay, or this is rarely pushed, you know. So, this is above the bath, but as we will see later on that when you lower it and the slag becomes a foamy slag, then that tends to engulf the electrode itself, that we will see later on. But as such, in the beginning, when you have the solid scrap which is charged into the furnace, the scrap needs to be first heated to say to the melting temperature. So, if you that calculation you can very well do. So, if you take 20 tons of scrap, so you multiply 20 tons of scrap multiplied by the specific heat of the scrap multiplied by the temperature difference that you are charging it at room temperature, and then taking it to the melting temperature, you can calculate the heat. And depending on the scrap composition, we can say that 400 to 500 kilowatt hour per ton is consumed to just melt the material. And then of course, once it is melted, then you have to do the refining can proceed, and all through this period of time there are going to be heat losses also from the furnace itself. So, on top of the bare minimum heat, and you know this is the melting heat, you will require, depending on the furnace, somewhere around 150 to 300 kilowatt hour per ton of steel. That is the kind of, and this is the refining requirement, depending on, this is the melting requirement of power in the system. So, you have, for example, off gas. So, the off gas goes out through this, and it's kind of not perfectly sealed, okay. The roof really sits over it, and there are loose contacts. So, ingression of air etc. can really take place into the furnace. So, this is the off gas, which this off gas, of course, just like any other steel making process, will contain carbon monoxide and carbon dioxide. So, the heat is convected, advected as well as radiated to the metal, and that is how the metal gets progressively heated up. And there is, of course, in AC furnace there is the charge does not advect conduct electricity as such. So, there is no what we call Joule heating, which is I square R. Okay. On the other hand, if you take DC furnace, then in that case what happens, you have one electrode here and the bottom anode is here, the cathode is here, and through the charge the electricity conducts. So, the arc between the metal scrap and the electrode, as well as the resistance heat which is developed due to the resistance of the charge, they will contribute to heating of the material in DC arc furnace. So, the operation of the DC and AC arc furnaces, of course, is quite a bit different. Here there are 3 electrodes, 3 phases, and DC we have anode and the cathode located, and between the anode and the cathode you have the metal or the solid charge, and therefore, the mode of mechanism of heating, the time required or the efficiency of heating etc. are different in the 2 furnaces. DC furnace and AC furnace both are popular in the industry, okay, and you have there are advantages of DC furnaces. Tends to be I believe more expensive, they are less noisy, they are easy to operate, but the cost of the furnace is building of a furnace becomes more expensive. AC furnaces, at least I have seen them to be quite popular in the Indian context. So, and you have here what is known as a tap hole, and this is called, all the modern furnaces will discuss this. Earlier the furnaces used to have a spouting leaf, so the furnace could be tilted a little bit and then the molten metal could come out of it. but these days this is not there. So, tilting arrangement for tapping is not there, but the tapping is done through EBT, which is called eccentric bottom tapping facility. Okay. So, the roof, hearth and electrodes are the main components of an electric arc furnace. The electrodes are basically made of graphite because of conductivity reason, and because graphite also has some finite resistance. So, enormous amount of heat develops in the electrode itself. The electrode becomes after some time red hot. They are water cooled, and because they are water cooled, the atmosphere contains really quite a bit of moisture at any point of time, and therefore, the electric arc furnace still are susceptible to more hydrogen content, and you can get about in BOF steel making, while you can get 1 to 2 ppm of hydrogen, in arc furnace steel making getting 5 to 7% hydrogen, 5 to 7 ppm hydrogen is quite frequent. Okay? And therefore, this is a big problem, and as I have indicated during one of the earlier lectures, that for critical applications hydrogen is not allowed beyond 1 to 1.2 ppm, and therefore, if the steel contains 5 ppm hydrogen, there is a necessity to have a subsequent dissolved hydrogen removal step. So, that we must remember, and the principal source of hydrogen is due to the water cooling of the electrodes. These electrodes are very expensive item. By the by, these furnaces are all basic furnaces. There is no acidic furnaces. In acid lining is much more cheaper than the basic lining. Acid lining basically material could be your silica lining, which is substantially more cheaper than magnesite lining, for example. So, if you go to foundry industries and you see electric steel making arc furnace, which is used predominantly as a melting unit rather than a refining unit, because the moment we say it is a refining unit, we will try to monitor maneuver with the slag basicity, etc., and then if the slag we make basic, then we cannot use an acid lining, because the lining will get eroded or eaten up by the basic constituent of the slag in no time. So, in steel making industries, all arc furnaces are going to be lined with basic material, and the hearth is basically lined with magnesite. On the other hand, the roof is different kinds of material is going to be used, mostly chromites as well as magnesites materials are used. They have their different requirement, as I have indicated, in terms of this region possibly is more important for corrosive action of the metal. On the other hand, the thermal resistance or the heat resistance of the roof is going to be far more critical, and that gives us or tells us the reason why different kinds of refractory materials are used in different systems or different parts of the furnace, roof as well as the hearth. These graphite electrodes are very expensive, as I have indicated, and the graphite basically undergoes quite a bit of oxidation. There is mechanical degradation, of course, and you have arrangements, this very coupling arrangements here, screwing arrangements. So, upper part is not replaced. I mean, if the lower parts which comes in contact with the molten metal or is exposed to a more harsher environment, if the lower parts gets consumed, in that case one can unscrew the lower part from the top part and then bring in a fresh lower part and then screw it on to the upper part. So, there are what do you call coupling arrangements, so that the upper and the lower part can be combined with each other. So, that is just for convenience of operations. So, these are expensive material, have finite resistances, and oxidation, mechanical loss, and oxidation particularly it can get oxidized with although carbon monoxide will be evolving, but we have some oxygen partial pressure that can react. But most importantly, that part of electrode which comes in contact with the slag, and particularly in electric arc furnace steel making, there is a practice called foamy slag, and that foamy slag is used the slag is formed and such that, so this becomes basically what it is done is into the slag we introduce coke powders or small chunks of coke. Okay? And the moment we put in coke into the slag, then what happens? Slag contains iron oxide, FeO, we know steel making is an oxidizing process. So, the slag in any steel making process will contain a significant amount of iron oxide, be it BOF steel making or arc furnace steel making, and there we will see that once we inject carbon into the slag, then the slag tends to foam. Why? Because carbon monoxide bubbles are continuously generated. So, there is a volume expansion, and that basically covers up the tip of the electrode as I have indicated here. Okay. And so, the slag also comes in contact, and then the same reaction, carbon coming in contact with FeO of the slag and producing carbon monoxide, the slag gets eaten up, slag tends to eat up the graphite electrode, and that is called So, the oxidation are two folds basically, with atmospheric oxygen as well as during the foamy slag practice, and mechanical degradation is another. Wear and tear during the handling and so on. So, and if the you can see that basically this tips it will go it will happen something like this. This shape will tend to get. This is the kind of shape that the electrode is going to really take after some time of operation, because this is the part which has been exposed, and the diameter of the electrode as well as the current density are two important parameters in this particular case, which control that what will be the heat which is going to be developed, amount of heat which is going to be developed in the electrode itself, what is the kind of erosion, what is the kind of electric heating efficiency, and as I said that there are two important parameters to this end are basically the diameter of the electrode and the current density that you apply. An electric arc furnace, as you have seen that I have noted down the value here, that you can have small furnaces where the rate of power supply could be about 500 kilowatt at the rate of kilojoules per second per ton of steel. It is a small furnace, and there are bigger furnace where we can have 900 to 1000 kilowatt per ton. These are called ultra high power furnace. You can imagine almost twice the rate at which the electric energy is being fed. So, you can this amount of energy, which is the melting heat, can be supplied in this furnace at a very fast rate. Okay? And therefore, you can have huge electrical paraphernalia attached to an electric arc furnace, huge transformers which can give rise to this kind of a power input to the furnace. So, we will have along with this for example transformers, the off gas as usual it contains dust etc., and most importantly the off gas in this case, because we are using scrap, can contain dangerous elements for example. Okay? So, I know of a case where chromium the scrap contained chromium, and then because of the oxidation environment, okay, what happens is the exhaust gas was found to contain hexavalent chromium, which is a very dangerous species to work with. So, the off gas treatment is very important in an electric arc furnace, because your basic raw material which is DRI or particularly scrap, and this scrap is coming from diverse sources. It can have different kinds of elements. We will analyze all those elements which are present, which could be present in scrap, and because we are buying from the market, these scraps therefore can contain volatile elements, carcinogenic elements, and all these kinds of things, particularly when volatile they tend to go out with the off gas, and then it is to be handled very carefully. So, we have an efficient gas cleaning plant also, along with we have scrap, these electrodes are attached to the scrap, so attached to the roof. So you can, the robotic arm which is placed like this, it can swing and then take the entire electrode attached to the roof, exposing the top surface, and then from the overhead crane you can charge the scrap into the furnace itself. And there is also there are buckets actually in which scraps are used. So heavy scraps are at the bottom and lighter scraps are, the heavy scraps are at the top and lighter scraps are at the bottom, so that when melting starts, you get some kind of a recirculation. So boxes packed with, with compacted scrap, they are actually suspended from an overhead crane, and the moment the roof goes away, moves away, and then the scrap is charged into the furnace, and then the roof is put back, and then one starts, pumping power into the furnace, and that's how the melting or heating of the charge is initiated. So you also have, for example, in many of the furnaces, oxygen. But before that, I think I would like to say that obviously you will have to have, material handling facilities, that you have to have scrap handling facilities, scrap charging facilities. You will also have to have liquid metal which is to be further processed, and treatment of the slag. So the slag metal handling capacity as well as the raw material handling capacities are also there. So gas kilning plant and material handling facilities. Now you have arcing here. So what is the source of stirring here? We all know that steel making will not happen efficiently unless and until there is a good amount of stirring in the bath. Okay? The arc is, does not cause much amount of stirring once, of course, it is melted. Okay? The arc cannot cause much amount of stirring in the system itself. So there are, 40-50 years back, there used to be what is known as an oxygen lancing facility. So you have a lance, and that lance is basically, it is a retractable manually operated lance, and that lance is inserted, and through this lance the oxygen will be pumped into the system. In good olden days, iron ore used to be the oxidizing agent, but that using iron ore will take the melting time anywhere between 8 to 10 hours if you want to process 50 or 100 tons of steel, hot metal scrap in the furnace itself. So to expedite the rate of stirring and to supply oxygen also more efficiently, because if you want to oxidize metalloids, okay, which are there in the metal, in the scrap, some little bit of refining out in DRI, you have to have an oxygen source also. And as I said, that in the good olden days you used to use iron ore as the oxidizing agent, but now nobody uses iron ore. Intermediate period, about 30-40 years back, oxygen lancing started, and this oxygen not only produced, supplied the oxygen necessary for metalloid oxidation, but it also produced the necessary amount of stirring in the system itself. Today, all the electric arc furnaces are equipped with bottom stirring mechanism. This has been borrowed from the bath agitation process. We have seen from the bath agitation process that a little bit of argon injected through the porous plug is going to be extremely beneficial as far as bringing the system to equilibrium is concerned, as far as reducing the loss of FeO in the slag is concerned. So therefore, bottom stirring facilities are a part, integral part of modern day steel making and so on, and that we have an oxygen lancing facility. So there is oxygen plant also. So now we can see that, well, we have no blast furnaces, no stoves, so entire iron making is not there. So we have a steel making unit or furnace which requires transformers, gas cleaning plant, oxygen cleaning plant. Not too much of a space is necessary, okay, in comparison to the basic oxygen steel making, because blast furnace necessitates that for a single big giant blast furnace you have to have not one converter, but you have to have 4 converters, to be able to consume that much of hot metal which is produced from one big blast furnaces. So, in a small steel plant, as you can see here, you have a small unit of electric arc furnace, and then you have subsequent processing which is common in both. It's a very simple step that we will see later on, secondary steel making. So, where you can remove hydrogen, you can adjust the composition, etc., and then you have a continuous casting setup. So, what we see as opposed to an integrated steel plant where you have a sintering plant, where you have a coke oven, where you have a blast furnace, you have several basic oxygen furnace and then secondary steel making, continuous casting, as opposed to all this paraphernalia in integrated steel mills. We will see in a mini mill or a special steel plants that it's in a very small place. You will go to Pune, for example, and find that the Kalyani Carpenter is located right in the heart of the city, not far away from the downtown area. Of course, the downtown is evolving there. Earlier, previously what was downtown, that was quite close to that Kalyani Carpenter plant, and that has been possible because the space requirement, the land requirement has been extremely small. So, and similarly, you can go also to Kalway plant of Mukund, which is not in a very remote area, like for example, when JSW started, it started nowhere, in Turangalu, where there is nothing at all, because you cannot get that kind of a land which is necessary to produce 20-25 million tons of steel through an integrated platform. So, with this background, we can see now that there are distinct advantages of setting up an electric arc furnace, and one such advantage is we have a small capex requirement. Capital expenditure is small capital expenditure. That is one important. This is apart from this, you can produce here diverse grade of steel, and the raw material at times is cheaper. For BOF steel making, what is the raw material? The raw material is the hot metal. So, the price of hot metal and scrap, you can buy certain quality of scrap really cheap, and that gives an edge, because if the final product of the final steel is is not economically favorable, in that case you will not be able to solve you can sell the product in the market. And the disadvantageous point is that I think in the case of electric arc furnace, you have disadvantages with respect to BOF. So, it has I think 7.6 gigajoules per ton of steel versus 16.2 gigajoules per ton of steel. This is electric arc furnace, and this is your BOF steel making, and the energy intensive process, because in the blast furnace, in the BOF process you have to break so many bonds, iron oxygen bonds, silicon oxygen bonds. So, the fuel requirement or the energy requirement is 16.2 by the way, it is enormous there. And even despite the fact that oxygen steel making is autogenous, the BOF integrated steel mills, the energy requirement becomes higher because of the blast furnace process itself. But that blast furnace process is not there, and even you are supplying electricity to melt and refine them all in the scrap requirements is very, and the process is very versatile. Lot of modifications are possible. One such, several modifications I have told you. One such modification is an ultra high power furnace. The other modification could be the what you call usage of oxygen from the bottom, and you can have many, for example, the scrap that you charge here. Another modification you can visualize is that you are not charging scrap at room temperature, but you are preheating this off gas which goes out at a very high temperature, okay, because the furnace environment is 1600 degrees centigrade. So, it can go up 600, 700 degrees centigrades for sure, and this heat which is there contains the sensible heat, particularly the sensible heat can be used to heat the scrap itself, and that scrap can be directly fed, just like the way I taught you during the mid-rex process, that you have the mid-rex pre-reduced pellets which are produced from the mid-rex furnace, and then you charge it directly into the steel making furnace, so that the sensible heat which is contained in those pre-reduced pellets can be utilized, and you can significantly bring down this energy requirement if you use hot DRIs or hot scrap into the system. And that hot scrap is not becoming hot because of usage of electricity, but it is this heat which will otherwise be lost, the sensible heat content in the off gas which otherwise will be lost, and that heat, if you through some arrangement will study that. So, analogous to a hot link process of DRI making, there is also an equivalent process here. So, if all you can incorporate all these things here, in that case the EAF and the BOF can be, UAF can compete despite small volume of production of only 1 million ton per annum, it can compete with a larger steel bigger size steel plants which produces maybe 10 times more than that, and this is possible because of all these kinds of advantages starting with. So, if you borrow money, the interest rate is going to be much smaller, okay. So, then you have to pay back period is going to be smaller, and if you can produce special steels as opposed to carbon steels, then possibly the payback period can still be reduced. So, there are many advantages and the land requirements, and today I think people visualize that electric arc furnace with an endless strip casting process, which we will discuss later on, can really revolutionize the steel making technology. But for that you will require huge amount of scrap, and you will be surprised to know that although we do not have a very good scrap collection facility in this country, and the resources in terms of availability of scrap, I do not know how realistic data are available, but countries like Japan, US, etc., and even China, billions of tons of scraps they have really amassed, and those can be effectively steel is, by the way, that, and I have told you in the beginning, in the introductory lecture, that it is the most recyclable material. So, the scrap material can be directly used when the iron ore grade etc. goes down, and then the hot metal prices are going to shoot up, and then one will see that even inefficient arc furnace may become, with an endless strip casting machine, a viable technology for steel making. But for that you will require huge amount of scraps, and there are many countries who have consolidated large volumes of scrap in anticipation of the future crisis, particularly in terms of the grade of iron ore which is fed into the BOF steel making process in the blast furnace. So, and that is why the arc furnace while open hearth have phased away, Bessemer process have faded away, could not compete with the BOF technology. Arc furnace is going strong. Over the years 30 to 35% of global steel is being produced, and as I have indicated that they produce a diverse grade of steels. For example, ball bearing steel, free cutting steel, then tool steel, all these kinds of steels which are required in small volumes, which cannot be prepared in a 300 ton converter because there is not that much requirement for any given customer. So, arc furnace becomes a viable unit for producing such diverse grades of steel in limited quantity. Now, having given this background about the construction features and operation, I will now like to discuss about steel making in arc furnace. The heat preparation is more or less the same, that once you make a steel, these furnaces, by the by, they while the BOF converter can be tilted almost by 70 to 75 degrees in order to tap the molten metal. These furnaces are not tiltable to that extent. Okay? They can be tilted for example by 8 degrees, 10 degrees, or at the most 18 degrees or so, because to drain out the molten metal through this eccentric bottom tapping facility. So, they during the process itself they are when they are dismantling, that is a different issue, but during the process they are going to be only marginally tilted, okay, in order to facilitate charging of hot metal as well as draining of molten material itself. But BOF, because they have a tap hole located here, as I have indicated, okay, this is the tap hole in BOF, so it needs to be tilted quite a bit. Why there is an EBT and we do not tilt the furnace to tap molten metal, that will be discussed later on when I deal with the tapping operations and the role of the oxidizing slag in the performance of subsequent steel making processes, particularly the secondary steel making processes. So, the heat preparation per se need not be discussed. Okay, it is the same thing that once heat is made, you inspect the furnace, if there is some kind of a damage, and then you repair that, and then you make it vertical, or you make arrangements for charging of the material. You charge the scrap is going to be charged, as I said. The entire upper part of the furnace is available the moment you have moved the roof away along with the electrodes, and from the top you can charge the material. And if you are charging hot metal, that hot metal can be charged from the side itself, and then the roof can be brought back and blowing of oxygen can be started. Oxygen, if you start right from the beginning, that can expedite the melting rate also, because in the presence of oxygen what happens is high temperature and oxygen, so iron will scrap will try to become, some scrap will try to become iron oxide and generating heat also. So, the oxygen lancing can also expedite the heating rate in the furnace itself in presence of electricity and a high temperature. Okay? So, and then you can make the steel and then you tap it. After tapping you can tap metal, and then subsequently you have only one, and tap the remaining slag, inspect the surface. Similarly, here also, as you can say, we have a working lining and we have a permanent lining of the base. The same kind of a construction goes on, and as I have indicated earlier, that they are all basically basic material. Here it is magnesite based, and at the top it is chromite based magnesite for the roof because of different thermal requirements. The scrap that we use, DRI, as we know that DRI can also be used, and these DRIs could be gas based and coal based. And because these are there is quite a bit of, if you have taken coal based, then what happens is in the DRI quite a bit of impregnation of carbon takes place. So, via the DRI you are charging carbon also into the furnace itself. So, merely charging DRI towards the later part can foam the slag, because there is a good amount of carbon which is present there. Degree of metallization possibly is better in the gas based. So, gas based DRIs are a little bit more pricey than the coal based DRIs, and this is simple because of the fact that you have a higher degree of metallization in gas based system, gas based DRIs. So, other than DRI you are going to use scrap, and of course DRI will contain those things which are there in the ore, like some alumina, some silica, and these are not going to be reduced because we do not have any reducing environment here. So, whatever oxides are going to be there, those oxides are going to be you have Fe is there, FeO is there. If FeO is there, FeO will undergo so there is carbon, some amount of reduction, some amount of FeO can go to the slag itself. So, the moment you add DRI, you must understand DRI is a cheap material. Okay. So, if the FeO from the DRI goes to the slag, then that means the slag has now a high potential of FeO. So, it will prevent the further oxidation of melt iron, and thereby what it is going to do is it can ensure that the dissolved oxygen level in the bath is going to be now a little bit smaller. So, whatever are oxides material present in the DRI, most of them will try to go into the slag, barring the iron oxides, a part of which can get reduced also. As far as scrap is concerned, the scraps can have different kinds of materials. As for example, you can buy a scrap which, for example, may be a machinable steel, so which may contain large amount of sulfur, maybe some grade can contain large amount of lead. You can buy stainless steel scrap which can contain nickel, which can contain chromium. You can buy ball bearing steel which can contain lot of manganese, etc. So, the scrap, diverse grades of scrap is available in the market, which is the principal feed material for electric arc furnace. Now, we can classify the scrap into 4 different categories. Scrap sorting yard is a very important exercise, and the scraps are sorted out in terms of their composition. So, what is the composition? The testing of the scrap, chemical determination of chemical composition, and then sorting of the scrap is a very important exercise in arc furnace steel making. One is that the scrap containing volatile material, for example, completely volatile material. If the scrap contains calcium, for example, at 1600 degree centigrade, calcium is in the gas phase. So is zinc. So, I would say zinc is a volatile material, calcium is a volatile material, and so on and so forth. Then we have completely oxidizable material. Oxidizable material. So, volatile material in the scrap. So, the category 1 scrap containing volatile material such as zinc, cadmium, etc. Category 2 scrap containing completely, so we are sorting the scrap containing completely oxidizable material, and completely oxidizable material we can say aluminum is one material under steel making condition, and we have seen that under steel making condition all silicon from the silicon removal curves possibly, and we can add all those elements whose position in the Ellingham diagram are between the aluminum and silicon line. Possibly we can say titanium oxide is, titanium is also one more. Partially oxidizable material, partially oxidizable material. Elements such as chromium. That means partially oxidizable material means this material will oxidize, they are not volatile, they will oxidize. So, if they are not removed to the gas phase, where will they go? They will go into the slag phase. So, partially oxidizable material such as chromium, if phosphorus is there in the chart, phosphorus will also partition, okay? Some will remain in the metal and some will go into the slag. And number 4, we will say that non-oxidizable material is also one possible. Non-oxidizable. These are the materials which have very low affinity towards oxygen. That means, all those elements whose position is on the top part of the Ellingham diagram such as copper, okay, nickel, etc., which has you cannot treat all of them together, okay, then you will jeopardize the operation. So, for example, if I use non-oxidizable elements, we must understand, I will just finish at this point, you can take, I have stainless steel, for example, I take stainless steel scrap, and the stainless steel scrap, if I want to make a different kinds of steel, for example, from that, it is not going to be possible, and suppose that steel does not want any, we do not have to have any nickel in it, but we know stainless steel contains 8% nickel or so. So, therefore, all the nickels are going to remain as residual elements because they are non-oxidizable. So, my final product is going to be then contaminated with nickel because I am not able to eliminate. So, therefore, what final product, what grade of final product you want to make, that will decide that which kind of a scrap you should be able to use and not. So, volatile material, for example, zinc, calcium is there, you do not have to worry, you can make any kinds of steel because they will be driven out, but you will require that even lead So, lead vapors can be high vapor pressure of lead is also going to be there. So, therefore, these can all be driven out, but this treating of scrap containing volatile material will warrant that you have a very efficient gas cleaning apparatus which will be able to filter out all these things. We will continue our discussion.